Thank you so much for the invitation and for accommodating online. I wish I could be with you. I want to acknowledge my student Aida, who helped prepare this presentation. So in our traditional approach to quantum field theory, we typically start with a Lagrangian, we derive Feynman rules, and from that we get the amplitudes, and that goes into, of course, calculating the observationally relevant, experimentally relevant cross sections. Any symmetries of the Lagrangian are inherited as properties like water densities and solved theorems of the amplitudes. One of the things we can do with the modern on-shell amplitudes approach is to turn this upside down. We can start by taking the physical observables as the fundamental quantities and compute those directly without reference to the Lagrangian in many cases, and then impose consistency on them in order to, for example, compute consistently the amplitudes of models without using the Lagrangian and Feynman rules or any redundancies associated with that. We can use it to explore the possible quantum field theories given spectrum and symmetries, and we can derive general results in EFTs and in particular effective field theories, which is of course the main focus of this talk. So in effective field theory, we learned that we work to a given order in the derivative expansion. We must include all higher derivative gauge invariant local operators that are permitted by the symmetries of what we're interested in. So a Lagrangian formulation is how many gauge invariant local operators are there, but we want an independent set. So we must eliminate redundancies from integration by parts in the action, redundancies associated with equations of motion when we're evaluating these operators on shell, as well as the redundancies of field redefinitions. And the on-shell approach for amplitudes lends itself very well to this problem. For instance, it immediately eliminates any redundancies associated with field redefinitions because the amplitudes just don't care about that. So the problem becomes a question of finding the one-to-one. So there is a one-to-one correspondence between on-shell local operators and the on-shell matrix elements. And so the amplitude formulation of the problem of finding the basis of operators at a given order is how many independent on-shell matrix elements are there modular momentum conservation, which is the equivalent in Lagrangian language to integration by parts. The on-shellness is just the equation of motion part, and we already talked about how field definitions are eliminated. We have to impose things such as both Fermi symmetry of identical states and so on, but that is straightforward to do at the level of amplitudes. And let me try to illustrate this in a couple of examples. So suppose we're interested in scalar operators with 4 abelian scalar fields dressed up with some derivatives. At the level of Lagrangian, I have to figure out where to put my derivative and in how many ways I can then contract the Lorentz indices. And then I have to worry about moving the derivatives around with partial integration and find independent terms. In the amplitude language, this is very simple. I simply have to find symmetric polynomials of degree k in the Mandelstam variables st and u, subject to momentum conservation s plus t plus u equal to 0. I'm taking here the massless limit. Now, such polynomials are always of the form s times t times u to some integer times s squared plus t squared plus u squared to some integer power. So the problem of counting operators simply becomes the question of in how many ways, how many k degree k polynomials are there? So in how many waves can I partition the integer k into 3 times an integer n1 plus 2 times an integer n2? And so just to an illustrative example, if I had 22 derivatives, the mess of figuring this out at the level of Lagrangian is not as much fun as saying that k is just 11. That means n1 must be odd. It'd only be 1 of 3, so therefore there are 2 such independent operators. It gives us more than the counting. It actually gives us the matrix elements, so we don't need to reconstruct the operators for applications in physics. The lesson is counting is easy, direct construction of the local matrix elements is easy, and basis changes are also easy, of course. Now, you may not care about 22 derivatives on 4 scalars. So let's take an example where we have some other particles involved. So here, an operator with 2 fermions, 2 field strengths of, say, it could be a photon or a gluon, and then 2 identical scalars. I can put some derivatives in that operator, and then look at what I get. So let's just focus on everything for simplicity being massless, and a particular helicity sector where the fermions have opposite helicity, the vectors have opposite helicity, and I have my 2 identical scalars there. So look at these 6 particle matrix elements. The spinor helicity formalism is extraordinarily efficient for figuring out answers to these kind of questions of how many operators are there. So there are no operators with an even number of derivatives on. That's a simple thing you could see by spinorizing all the indices. and having to find some Lorentz invariant contraction of them. So the first and lowest operator for which this exists has one derivative. That's a dimension 10 operator. And it takes less than a second for my old laptop to compute that there are two such operators. Going to the next order, dimension 12, there are 21 operators. It's a matter of seconds. Dimension 14, 114, done on my own funky computer here in 5 minutes. Now, nature is not all massless, so we of course want to also understand this for massive particles. And that uses the same principles and a little more machinery, and an obvious application there is standard model effective field theory. So recently, there have been many approaches to massive spin-holistic formalism, but a very recent and efficient way of doing it is Kani Hamad and Huang and Hang's paper from 2017. So the group by El-Khadra and collaborators in a series of papers have applied this to try to find systematic ways of using these methods to characterize 3- and 4-point standard model effective operators. There's only partial comparison from that particular group with the Lagrangian approaches, including 2 examples of Henning, Liu, Milian, and Moriyama. But there are a series of follow-up papers that do more systematic comparisons. There's also very recently from people at Queen Mary work that has goes to higher order and more systematic in comparisons. There are many other applications that I just list up here in the corner to apply these methods of using amplitudes method for determining local operators, everything from supergravity and into Born-Infeld, chiral perturbation theory, and so on. Here are just some of the names, but there are many others in this area, and including also ideas in dark matter. Now, an important thing for experimental connection from SMEF to the actual experimental results is to understand how these operators mix on the renormalization group. And so this is, of course, relevant for Merighetti's talk. So under the RG, the operators mix. And in particular, we can ask how the J operator coefficient, so it's coefficients CIs and J here, how the J operator affects the flow of the I operator under the renormalization group. And so here's mu is the renormalization scale. And that is encoded in the anomalous dimension matrix. So one interesting thing that was noticed about this were some surprising non-renormalization results for dimension 6 standard model effective field theory operators by Alonso, Jenkins, and Manohar in 2014. An explanation for these surprising results and non-renormalization properties were given by Cliff Chung and Shen in about a year later using exactly on-shell approaches. This was at dimension 5 and 6, but using new results of characterizing anomalous dimensions and beta functions developed by Kavan-Witt and Wilhelm, new renormalization theorems were derived by Barron, Parra-Martinez, and Sawyer at dimension 5 through 7. And they further also went to study the 2-loop anomalous dimension matrix. Very recently, just here in the new year, these was further extended results to the mixing matrix at dimension 8 by the group at Queen Mary.
3 minutes. Yeah.
Good. So there's also approach to EFTs that are very geometrical in nature, proposed originally by Alonso, Jenkins, and Manohar. And the on-shell amplitudes perspective has been picked up here. I'm mentioning 3 different groups who has applied on-shell methods there. There's another thing we learn about EFTs, which is that the high derivative operators that we have to include appear with generic coefficients that are naturally expected to be order 1 in terms of the scale of the UV physics. So if they're not 1 or much smaller, we have explanations to do. Or put in a different way, if these theories, these EFTs come from some sensible UV physics that has unitarity, Lorentz invariance, and locality, then it turns out to put constraints on the possible Wilson coefficients and their range. Exploring these bounds that come from such UV completability is the subject of the SMatrix Bootstrap, sometimes formulated as EFT hedron, and of course also closely related to the ideas of the weak gravity conjecture via amplitudes. Thus, a bottom-up, one application of this is a bottom-up bootstrap of string theory via amplitudes, and that's a very active area of research right now. And there's, by the way, a related Snowmass white paper on bootstrapping string theory by these authors here. There are many other interaction points between scattering amplitudes and EFTs. So here I'm listing just a few. For example, the ideas of soft theorems in effective field theories, and the idea of bootstrapping exceptional field theories, which are those of Goldstone bosons of various types. There's a lot of people who worked on that in different contexts. Then there's starting to be effective field theory showing up in the context of celestial amplitudes, which is a vast field. Here's just mentioned a few, one particular paper where EFTs come in. There's work on understanding the double copy in EFTs, how to include higher derivative operators in the BCJ-based approach to the double copy by Carrasco and collaborators. And with my collaborators, we have studied a KITP Bootstrap approach for how to generalize the KLT formula in a more general way, not just in context of high derivative operators systematically, but also just from the complete set of what does it even mean to have a double copy? What are the rules for generalizing how it works? These two approaches have begun to be connected. There's a very recent paper from December by these authors here that makes some connection clean at 4-point and start looking also at 5-point. And of course, EFTs will also show up in the context of amplitudes in gravitational physics, the connections to LIGO, and so on, as we just heard about in Solon's talk. So the on-shell amplitudes methods and applied in the context of effective field theory is a very active and growing field of research that is starting to attract a lot of young researchers. It has impact both on the front of our fundamental understanding of quantum field theory, but as I've shown you also, it has direct applications in particle physics in the context of standard model effective field theory, Higgs effective field theory, and so on. And I want to emphasize that these are the pillars in our field, the interplay between the pursuit of the mathematical truth and beauty that we love, but also the very important connection to experimental physics and particle phenomenology, which is what we have for describing nature. Thank you.
Thank you. Questions? Questions on Zoom? So maybe I will ask the question. So how realistic do you think it's going to higher orders in the standard model effective field theory using that approach? But at some point, you still hit some wall with just having too many kinematical terms anyway. Or do you think there are some like closed formulas, some all order characterizations?
So I think you can ask that question in many different contexts. I mean, you could ask it in terms of powers of G that is relevant for LIGO. At some point you hit the wall, and then when you hit the wall, that's the time to develop new methods, right? That's when you start thinking about how can I do something different to do this problem. And it's often in those situations that new discoveries are made. Like when you push to higher loops and supergravity calculations and perturbative supergravity, one of the things that came out of this was the BCJ formulation of double copy, which has had an enormous impact. So yes, at some point you hit the wall, but that's when you have to think out of the box.
Mm-hmm. Okay, thank you. Okay, more questions. Nathaniel has a question.
Great. Thanks, Henriette. This is Nathaniel Craig. Thanks for the great talk. One of the things that's been very interesting to me is the appearance of zeros in surprising places, as you summarized with the zeros in the matrix SMEF anomalous dimensions. And you know, as a particle theorist, right, looking for explanations of surprisingly small parameters in the standard model and beyond. Do you think there's anything that I mean, you know, so we see zeros now that go beyond one loop, that go to 2 and 3 loops in the amplitudes program, and they're all for sort of interesting and interrelated reasons. Do you think there's something that we can extract from that about some of the, for example, the naturalness problems of the standard model? Do you think there's something there?
I think that requires more input than just knowing some zeros. Knowing something about the values and possible ranges of the Wilson coefficients would probably be more information, give more information of that kind of problem. And I think that would be a very, very interesting thing to address.
Okay, thanks. Looks like we got a hand from Nima. Nima, go ahead.
Yeah, actually, I had a question similar to Nate's, but maybe I'll ask it slightly differently. Then I'll make a tiny comment about Nate's question. The question is, so I thought the kind of understanding at one loop was just that there are, you know, just like the all plus low-on amplitudes vanish for a reason that's not officially a symmetry reason. But anyway, we know it vanishes, and it's sort of secretly because of supersymmetry at tree level, amongst other ways of seeing it. But I thought that the explanations were like that. They're sort of the obvious vanishings of the obvious helicity amplitudes that vanish in cuts were the things that didn't show up in the beta function. Can you sort of I didn't study those great follow-up, those great later papers that went to higher loops in detail, but can you, if you were to sort of summarize, is there something that, is it the same kind of surprise that, is it the same fact that just keeps going further and further, or are there things that are more surprising from the, let me ask it another way. Are there ever cases where there are sort of combinations of cuts that give you 0 rather than a given cut that gives you 0 or something like that?
So that, I guess, is more a detailed question for the authors. I don't know if there's at this stage a systematic pattern, which I think is what you're asking, that could lead to some hidden symmetry or something like that, which would of course be really interesting. But I would invite the authors, if they're on here, to pitch in and say more about it. Okay,
Tsvivel.
Well, there were actually multiple reasons why it was happening. There was one reason which at the end was pretty simple, but it was surprising ahead of time. It was cases where you can write down Feynman diagrams, and if you did it the normal way, they would look like they'd look like there's a contribution. But when you did it in a much slicker amplitudes way, what you discovered that those contributions were all 0 scale integrals, and then you could argue that you get 0. So that some of the theorems had to do with very first contribution that you get, and for those cases it turned out to be 0. Then there were a collection of other reasons having to do with things similar to the helicity counting rules, but they would be active at higher loops. There were some color rules. There's a whole collection of reasons.
Okay. And the quick comment I wanted to make on Nate's question is just that there have been hidden symmetries that have shown up in amplitudes. There's a dual conformal symmetry. There's a sort of projective invariance I mentioned in my talk. What's interesting in all these cases is that the hidden symmetries, the teeth that they have, is that the amplitudes are better behaved at infinite momentum in particular directions in momentum space, not random directions, but in particular directions in momentum space are much better behaved at infinite momentum than you would naively think, and that individual Feynman diagrams would lead you to believe. So now, no one has yet turned that into anything useful for naturalness problems, but it is intriguing that the hidden symmetries do indeed involve something better at large momentum than you would naively have thought otherwise.
Great, thank you, Nima.
Okay, so thanks all the speakers of our session.